How is everybody today? Good. Questions about anything before we get going? Okay. Let me open it up real quick here. Yes, you want to do a ratio. Yep, absolutely. Correct. Yep. You and sorry, go ahead. No, go ahead. Right. So the reason why we would check to see if the variances are equal is to see whether or not that we need to worry about lowering our degrees of freedom if we were going to test a difference of means from a small sample. Yes. Yep, you're welcome. Other questions at all? No, you're just going to use the var.s to get your sample variance. Yep. And then use that, whatever that value is, to get your sample statistic that you need. Right. So when you're doing your sample, statistic, yeah, it's testing whether or not the sample variance that you're getting is consistent with a population variance of 210. Anything else? Did the video go okay that I asked you to watch? Yep. Okay, cool. Because, like I said, I just wanted to get the concept thing behind it set up so that we could spend the day just looking at Excel and how we'll use Excel to do this goodness of fit test. So, just to write it down again so that we can see what the computations are that we're going to be doing in Excel. That statistic that we talked about in the write-up was, it said it was a q sub k minus 1, and it looked like the sum from I equals 1 to k of y sub I minus np sub I squared over np sub I. So if the p sub I is representing the probability that you land in category I, if you will, then that n times p sub I is the expected number that you should see land in that category. And then the y sub I is the actual observations that you make to be actually a number of observations that you make that actually did land in that particular category. So those are the two pieces of that particular term. We're adding all of those up, and the derivation that I gave you in the video was to show you that you split it into these pieces, and you can rearrange to where it looks like this particular format. You end up with if these probabilities really are assigned the way they're supposed to be assigned, then this particular variable should be approximately a chi-squared of k minus 1 degrees of freedom. So this is how we're going to do the particular hypothesis test in this particular case, is that we're going to use this computation as a sample statistic and compare that value to a value that we should get from a chi-square distribution to see is this an unlikely number to get when we make that particular computation. Again, and then like I mentioned in the video, intuitively, the reason why we only have k minus 1 degrees of freedom, even though there are k terms in the sum, is because, of course, when you partition your population into these categories, if you've put in everything into k minus 1 categories, the kth category is completely determined. It's not really independent of the other ones. It completely is dependent on how you divided the things up into the other k minus 1 categories. So that's why you end up losing a degree of freedom here, even though you're summing what looks like k things that remind you of chi-squared ideas. Okay. So just wanted to mention that before we go off here into Excel. So let me see if I can share the Excel sheet. Yeah, absolutely. Yes. Yeah, because we would expect that if that piece of I really does represent the probability that a particular observation should land into category I, then the expected number over n trials should be close to the number of observations that you actually make. So this value on top really should be close to 0. If it really is truly you've had enough trials to determine whether or not that this really should be the case, then that number on top should be close to 0, because you would expect the number of observations that you see over n trials to be close to the expected number that you would expect to see in that many trials. So you would expect this to be close to 0. If this really isn't the way the probabilities are assigned, at least for one particular category, then you would expect that at least one of your observations relative to the expected value should be large. Now notice I said relative to the expected value. If this expected value is 3, then being 5 is a fairly large number. But if this expected value is 100, 102 is not that large relative to it, which is why we're dividing out by this. I mean, it turns out that that's what's happening, but you can think about it as that's why we're dividing out by this piece in the denominator, is that we see, we see that we're dividing out this expected value on the denominator to see if this is a big difference in a relative sense. In a relative sense, meaning relative to the size of the expected value. So we would expect that if this is true, in all cases, we would expect that all of these would be small, so that when you add them up, it doesn't get to be too large. But even if one of them gets to be large, then this is good. The whole sum will be large, and then we would expect that it's not really the case. Which is another reason why I mentioned in the video and in the book that you want to make sure that your NPI isn't very small, because you don't want to be dividing by a small number in your denominator here and making this fraction huge, even though you don't really mean it to. Pardon me. Sorry. Right. So let's go over to Excel here. I actually remember to share it this time instead of to start talking about it and not sharing it. All right, so let's look at this problem 8.1-3. It's in your textbook. So they give you 50 digits from the Michigan Daily Lottery. This should be one that was on Moodle. Is that not the one that was on Moodle? It should be the one that's on Moodle that's labeled 8.1. Should be. And you'll notice that I was smart enough to put all the different problems in tabs in a single Excel file rather than switching back and forth to multiple Excel files. I know. All right. Do I have multiple? I do not have multiple. This is the only Excel file that I have open currently. All right. So let's talk about how this works. So they've got 50 digits in a row that were supposedly randomly generated. So if they're supposedly randomly generated, we would assume that the probability of picking a particular value should be 1/10. So that's why the hypothesis, the null hypothesis here is that P0, P1 out to P9 is equal to 1/10. So hopefully I typed all these values in here correctly. I did it quickly last night, but it'll still illustrate the point even if I didn't. So anyway, the first thing if we have 50 digits and the probability of any individual digit is 1/10, how many zeros would you expect? How many ones would you expect? And so on up the line for each of those categories. What would you expect the expected value to be in a particular category be? 5. Good. All right. So the first thing I'm going to do is I'm going to make an expected column here. And I said that each of these should be 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So these would be the expected number of values. Let me add in a column here just so that I have a label here. So the digits that we can see are 0, 1, and then up through 9. All right, so these are I'll say these are the categories. These are the possible digits that we can see, right? So in this column, I'm going to call it the observed column. Those are the actual observations that we make to be in those categories. I'm going to use the COUNTIF command. In the COUNTIF command, and then there's also a COUNTIFs command, which I'm going to use in subsequent problems here. With the COUNTIF command, first you put in a range. So that's the range that I want. I'm going to make that an absolute cell reference because as I copy this formula down, I don't want that to change. So I'll hit F4. And I want to compare it to the value that's over here. I want to count how many zeros we have. Go back up there in case you're looking at the function again. So the first argument is the range of cells that you want to count the values in. And then the second argument is what I want, the condition that needs to be met to be able to start to add 1 to the counter each time. So in this particular case, it says there's 2 zeros in here, which I can actually see those pretty easily. All right, now I'm just going to copy this down so that it counts. Yes. Because the probability for each particular category is 1/10, and there are 50 observations. So I'm just doing the 50 times the 1/10. Yep. Yep, it scooched off the screen when I added the column in there, so that was why. Which column? This one? Oh, I went over and do you see how the white plus changes to a dark plus? Okay, so once I hover over that little box that's in the lower right-hand corner and make it turn to a dark plus, I just click on it and drag. And it just copies the formula down. Makes it go faster. All right, so then in this column, I'm going to do my individual statistics for those. So I want to do, this column is the observed minus, I'll just write it as O, observed minus expected squared over expected. That's what this column is, right? Because remember the formula was y sub I minus np sub I squared over n p sub I. So this is just observed minus expected squared over expected. So the observed is over in B8. The expected is over in C8. I'm going to square that and then divide by expected, which is in C8 again. And then I'll do the same thing. I'll grab and pull. So each of those are the individual values in that summand for the q sub k plus, q sub k minus 1. So since those are each of the individual pieces in the summand, I'm going to label it as q sub 9. The reason why it's q sub 9 is because there are 10 values and it's one less than that, because that's just referring to the degrees of freedom. You can label this however you want. I'm just labeling it with the notation that we used for the statistic. And the only reason why I'm using a q is because that's what the book uses. All right, so we want to add those up. So sum of those, I get 7.6. So this is our test statistic, what we just computed. Yep. And so that's just adding your observed minus expected column. Now, if we want to compare this to a critical value, we know that if these probabilities are true, then this should follow, this distribution of this q sub k minus 1 should follow a chi-square distribution on 9 degrees of freedom. So your critical chi-square value, we should be able to get from the chi-square dot inverse dot right tail. Always going to be a right tail test here because we want to know, does this summand get too big? It's always too big. It's not ever too small. So we're always going to use the right tail to get our critical value. Alpha here is 0.05. The degrees of freedom is 9. So the critical value is 16.92-ish. So in this case, as we do not reject, so all we're saying here is that as far as that particular conclusion would be, all we're saying is that there's not evidence that it's not random, right? That's all this is saying. But what we're really talking about here in this particular section is the idea of goodness of fit. This is a probability distribution. This is assuming that we have a uniform distribution, a discrete uniform distribution on 10 elements in your set, right? We're saying the probability of 0 is a tenth, a probability of 1 is a tenth, and so on up the line. So what we're really interested in knowing is this a good fit? Does this particular distribution do a good job of fitting the data? That's the whole point of doing this. It's not so much of, I didn't have enough evidence to reject that it's not doing a good job. I want to know, is it doing a good job? So really what might be giving you a little bit better idea of whether or not it's doing a good job is the idea of the p-value. How likely is this to be kind of a worst case scenario idea? If you wanted to go from this value or higher, what's the probability? So if I want to know the p-value, I would use the chi-squared distribution right-tailed. The x that I'm interested in is the test statistic up here, and 9 degrees of freedom again. So this p-value is about 0.57. So that tells you that it's not a bad fit. I mean, if you had p-values that were like 0.8, that's a really good fit, for example. But this is not a bad fit. So not only did we not reject H0, this is not a very unlikely value to have happened if it's random. So as far as we're concerned, we might as well just go ahead and say it's random. We don't have any evidence to say it's not random. And this p-value being this large is saying that I really have no reason to suspect that it's not random. Now, if that p-value were in the, say, the 0.2 range, then you might be a little bit more suspicious. But a p-value of being 0.57, that there's nothing there that's telling you that the distribution is not random in this case. This particular, no, it's in this particular case that they're saying the setup of the problem is that they're randomly choosing integers from 0 to 9. So that's the random idea. Yeah. So this one's, I wanted to go through this one because it was a fairly straightforward way to show you how to get these things set up in this case. As we go along, we're going to have a little bit more, as we're using other distributions to see if they're good fits, we're going to have to do a little bit more for setups. And I wanted to start with a basic example here, which is what this one was. But it was a little bit less basic than flipping a coin. All right. All right. So other questions on that? Yeah. No, but I just wanted to know. I just wanted to know, did the distribution of the digits look random? That was it. Yep. All right. So let's look at 8.1-8. This referred back to chapter 2, which the problem, I just wanted to give you the setup of the problem. It was background radiation detector for a given period. So this is a gamma ray detection experiment over 300 1-second intervals. So that's what all these values are coming from. I don't really care about that, but that's what these values are coming from. And it wants to know whether or not a Poisson distribution with gamma of equal to 3 is a good fit for this data. So there are 300 values here. They actually go off the screen over here to column T. You can see that. So I had a good time yesterday typing in data, as you might imagine. So anyway, let's talk about how we would determine if the Poisson distribution is a good fit here. So we've got values, it looks like, well, they're all single digit values, certainly. So the first thing I'm going to do is make my categories. And again, like I said, these are all single digits, so I'll use 0 through 9. And I want to see how many observations that we have of each of these. So using that COUNTIF command again, the range goes all the way over here to T15. And the criteria, sorry, I need to make sure that I make that an absolute cell reference. Yeah, I know I entered too few arguments. All right, so I want absolute cell references on those because I want to copy this formula down. And remember, Excel will use relative cell references unless you tell it to fix it. So what I mean is that when I say that the criteria is this one, the relative cell reference idea means that it recognizes that I clicked the cell right to the left of the formula. So when I copy this down to the next cell, it's going to go grab the value that's right to the left of that formula. So that's why I have to use absolute cell references for the range, because those values, I want to make sure that they're always referenced in that rectangle that we have up there. All right, so then again, I can copy this down. All right, so those are the observations, and I don't have anything here in category 9 at all. All right, so now I want to do the expecteds. So again, this said that this is a Poisson distribution with a mean of 3. So I want to know in 300 trials, how many times would I expect to see a value of 0? Well, the probability I can get from the Poisson distribution, the Poisson PMF. The value that I'm interested in is 0. The mean of the probability distribution function, or the probability density function that we're looking for, probably mass function in this case, is 3. And in this case, I don't want cumulative. I want the probability that I actually see a 0. And I want to multiply this by 300. That's going to give me my expected values for this, right? Because I'm going to do probability times number of trials. So again, Poisson distribution here, I want to know how many zeros do I see? How many zeros should I expect to see? So the probability that I see a 0 is given by this function, and then I multiply by 300 to see how many I expect to see. And let's copy that down. So over 300 trials, if I had a Poisson distribution with a mean of 3, this is how many we would expect to see in 300 trials. So now, if I do each of the individual pieces, so observed minus expected squared over expected, I will do observed minus expected squared divided by expected. And then pull this down. We're always going to use chi-squared to do the test statistic. That's always chi-squared. So they will always tell you what distribution to try to fit it to. But when you do your test statistic, it will always be a chi-squared test statistic. Every time. Okay. All right. So now if we do this, we can, let's see, this will be our test statistic. I'll put it over here. This, remember, your test statistic is just the sum of the values that you computed. And then if we want to do critical value, just bump this up a little bit wider. The critical value, again, we use the chi-squared distribution, the inverse. We're doing alpha equals 0.05 again, and there are 9 degrees of freedom on this one. And if we do the p-value again, I can do it this way. So in this particular case, again, this tells us that we do not reject H0 again. But we may not necessarily be exceptionally excited about that p-value. It's not horrible, but 0.5 is not a great one if we want a really good fit for this particular data. Now, one of the things that could be messing things up in this particular scenario is that when we're getting close to the end here, these values are really tailing off, right? So what we could have done instead of doing the counting in this particular case is the following. What we could have done is do values for 0 to 7, or values for 0 to 6, and then look for greater than or equal to 7 as our last one. Just put all of these observations in 7 or higher. make it a whole bin of things and do an overall computation of observed minus expected. So I can still copy this formula down here and pull this to here. This is just, all I did was just use the exact same formula that we did up here, because again, I'm counting, did I see a 0, did I see a 1, did I see a 2, and so on down the line. But to make a comparison of greater than or equal to 7, I've got to do a slightly different criteria. So I wanted to show you how to do that. I should say criterion, since I just have one of them. All right, so the range was still, if I remember right, A1 to T15. And I'm just typing in the absolute cell references. All right, so I want this to be greater than or equal to 7. So to do that, in this particular case, I should have not put that greater than or equal to sign in there. So this is going to give me an error when I do this, but I'm going to fix it in a second. So to put the greater than or equal to in, you're going to put that in quotes. So that's actually telling it, okay, I want to check it that it's greater than or equal to. So if you had less than or equal to, and greater than or equal to, you'll put that in quotes like this. Then you're going to put in the ampersand, because a lot of times you're going to want to compare this to a cell value. So the ampersand here is telling it, okay, now you're going to want a cell value, or I could actually type the number 7 here as well. But I want to go back and grab this cell reference, and I'm going to change that just to the number 7 after I hit enter here, because it's going to give me, it's going to yell at me. So I'll put a 7 in there. There we go. And so now it says that so the number of times that it's greater than or equal to 7 is 12, which we can actually see from that computation above. So again, the reason why we're putting them all in this particular case is because these values here are small, so that your these differences could get big. And they don't seem big right here anyway, but these differences can get big pretty quickly if we're seeing very few things, very few observations that are in a particular cell. And especially when these values start getting really small, then it can make the fractions really big as well. All right, so then if we want to do expected, let me do an intermediate step here and just show you what the probabilities are. So if we do the probabilities, I want the Poisson distribution. I still want to grab the x value that's over here. The mean is 3, and I still don't want it cumulative. I want the probability mass function. Now in this case, I'm just going to copy it down to 6. This last entry here should be 7 or more, which means it should be the rest of the probability, right? It should be 7 and anything greater. So for this cell, I'm just going to do 1 minus the sum of the probabilities that are in the previous cells. Okay, so I'm just using the complement idea for that. And then now for my expecteds here, this will be my expected values. I'm going to do those probabilities times the 300. Now notice that this value, when I get down all the way down to 6, should match the ones that were in the previous, when we did it the previous time. It's just the 7 will be a little bit different. So notice the ones down to 6 all match. When I get to 7 now, I see an expected value of 10. And now, if we do our test statistic, I want to add up all of these values. Oops, I added up. I didn't do my computation, sorry. That's why I got 300. I should get 300 out of that. All right, I need to do my observed minus expected squared over expected. Now copy down. And now sum up. Notice that test statistic is much lower in this case, that's a good thing. We want a small test statistic because we want it small relative to the critical value, which is, in this case, a little bit different because I've lowered my degrees of freedom. Since I stuck those last two groups in with the 7, I now only have 8 total groups, which means we have a degrees of freedom of 7 in this case. I still do not reject H0. That's still the conclusion. But my p-value now should be much better. This is my test statistic, and my degrees of freedom now is 7. Notice that p-value is now at 0.8. So that p-value, this particular fit is much, much better than what was previously indicated by the p-value. But that's again because we've been to these last ones because we have a small number of observations. In particular, we didn't see anything at 9. So we might as well just put everything in the 7 or greater bin with that probability. Notice it changed that observed minus expected value here. This one had a 3 in it to start with, plus these other 2 that we were adding in, and we changed that whole chunk down to a 0.378, 377. So that gave us a better fit for our data and saying, oh yeah, hey, look, it looks like a Poisson with mean of 3 really is a good fit here in this particular case. This one? Yep. Okay. Yeah, they should be different in this case because we lowered the number of bins. Lowered the number of categories. That's funny. It could. It depends on what your groupings are. For example, I'm guessing if you would have grouped the 0 and the 1 together and tried to do this, it probably would throw things off pretty good. Yeah, well, it might be an indication that you might want to try to group the 6 with something, maybe, is because of that number, that 2.28, is having a bigger influence on the test statistic than anything else. So, yeah, that's the kind of things that you would want to look for to see if it would help or hurt. I mean, that would just be things that you would be playing with. I mean, that's what a lot of statistics is anyway, is just massaging the data to get it to tell you what you want anyway. So that would be the kind of thing you would look for to see if there's a massaging to be able to do that in that fashion. Yeah. Well, you want to massage the data, but you'll massage how you're... you start rooting around in there. So... yeah, you want to massage the things around to see what's going on. Yeah. So, other questions on that one? It's called the goodness of fit test. All right. Let's look at the next one. So this is another one where we've got a Poisson distribution, but this one's slightly different because it's telling you that it says to use an estimate for 5.6 so we can use the table. I'm actually going to use that 5.59 value as our estimate anyway to see if we've got a good fit for this particular Poisson distribution. But there's a difference in this particular case than there was in the other problems that we've done so far, and the fact that in everything that we've done so far in the video and in the previous problems that we've done, they told you a specific distribution to try to fit it to with the specific parameters given to you. So in the video and in the first example we did, we were given the specific probabilities. In the previous example, it said fit it to a Poisson with a mean of 3. You were given that parameter, which in a sense gave you the probabilities. Now, in general, if you're doing these problems, you're not going to be given a specific parameter to try to fit it to. You're going to try to guess the parameter based on your ideas of doing estimators that we've done in the past. So if we're going to try to estimate a Poisson parameter, well, the Poisson parameter is the lambda. Your maximum likelihood estimator for lambda is the mean, the x bar. So you're going to use whatever your sample mean is, which in this case is that 5.59, that they told you it was 5.59. This is what you're going to use as your mean for the Poisson distribution to see if it fits that particular mean. However, once you estimate a parameter, and this is beyond the scope of what we can actually prove in what we've learned so far in this course, but once you estimate a parameter, you lose a degree of freedom. So when you do your chi-squared test, every parameter that you have to estimate by a sample statistic loses a degree of freedom. We've seen something like that when we did estimating the population variance using the sample variance. That had a chi-squared, well, a multiple of it has a chi-squared distribution on n minus 1 degrees of freedom. You lose 1 because you're basically estimating the population variance from the sample variance. It's the same kind of concept when you're doing these goodness of fit tests. When you estimate a parameter using a sample statistic, you lose a degree of freedom. So when we do these into categories, whatever number of categories you have, you automatically subtract off 1 from the degrees of freedom, because once you fill in k minus 1 categories, the kth one is automatically filled in, so you lose 1 there. And then every single time you estimate a parameter based on your sample, you lose another degree of freedom. So in this particular example, we're going to estimate one parameter, the lambda, based on the sample. So we'll lose a degree of freedom there. But things like if you had a gamma distribution where you estimate 2 parameters, the alpha and the theta, if you're using the sample to estimate those two, you will lose 2 degrees of freedom. If you do try to fit a normal distribution and you estimate the mean and the variance based on the sample, you lose 2 degrees of freedom there as well. So that's just an important concept. Again, the proof of that's beyond what we can do right now. So there was a professor back when I was a student who used to say, believe it or flunk. So that's kind of where we are with this, is believe it or flunk. We don't have enough machinery to prove it right now. But you can kind of understand why that might be the case, right? You're not using the full information about the population. You're only using information that you can glean from the sample. So you lose a little bit of freedom when you do that. That's kind of the idea. All right. This one gives you a little bit of a hint on how you might want to try to group some things. This one says group everything that's x less than or equal to 1 into one category, and everything when x is greater than or equal to 11 into another category. In particular, notice that there were no observations for zeros here, right? So it says go ahead and just group everything less than or equal to 1 in one category, because that would include your 0, which there weren't any observations anyway. And 11 and 12 are pretty small, so it says group those together as well. So these were your observations. But remember, this first one, we're going to do less than or equal to 1. And for 11 and 12, we're going to do greater than or equal to 11. So for the first one here, for your probabilities, I'm going to do the probabilities first, and then we will do the expected values, or the expected number of observations. I want to use the 1 here. The mean we're going to use is 5.59. And actually, I could have done a weighted mean here. Actually, let me just do that first, now that I'm thinking about it. So I want to do a weighted mean here. So I'm going to multiply these by these. So I'm using the sum product command. what that sum product command does is basically a dot product. It takes this times this, and then adds this times this, and adds this times this. That's what the sum product command does. And then I want to divide that by, that might be actually equal to 5.59 now that I see that. I want to add this to, or I want to divide this by the sum of these. And I'm going to bet there's 100 here. Look at that. All right, so then in the average here would have been this divided by this. The only reason I did that was because if you're given data, you're going to have to compute the mean. In this case, it was given to you by number of observations rather than actual values to compute the mean. That was why I did a sum product to get the total and then divide by the number of observations. All right, back to what I was doing. I didn't know if they rounded or not. I was trying to show you how to do it in case it was rounded. I know it was right there. All right, so I didn't know if they rounded, and if they had rounded, I wanted to use the actual better approximation than what they gave in the problem. All right, so for this one, remember we want less than or equal to 1. So I use the A1. Here's the average that I want to use, and I'm going to fix that with an absolute cell reference. And again, if you have a set of data where you compute the average, you can do that as well. Compute the average and then just go and grab it and then fix the cell. In this case, I want it to be cumulative because I want to include the 0 in there as well. So that'll be true. The next one, however, I want it to be false. So this with this mean and false. I'm going to copy that down to 10. And then this one needs to be 1 minus the sum of the others. And I need smaller fingers. And again, if you add up those probabilities, you should get 1, obviously. Now when we do our expecteds, this should be this, and we just said there were 100 of those, so there'll be this times 100. And copy this down. And now this one should be your observed minus your expected squared divided by your expected. And copy that down. All right, now add these up. That gives you your test statistic. So we get 7.04-ish. Again, our critical value. I hate automatic substitution. That chi-squared inverse right tail. We're doing 0.05 again. Now, okay, so how many bins total do we have? We got 11, right? That's the total number of bins, total number of categories. We lose 1 automatically off the top, so that's at 10. We lose another 1 because we're using an estimate for the mean as the population mean. So this will be degrees of freedom is 9. What do you mean? I'm sorry. I meant off the top. You automatically lose 1 by the way we're doing the goodness of fit test. That's what I meant. Sorry, I said off the top, and you were thinking at the top of the data. No, we lose it off the top just from the start. We always lose 1. Sorry, that's what I meant. And then if we do the p-value again, do the p-value on that on 9 degrees of freedom. So we get 0.63, which is a pretty good fit. So this particular, whatever this data came from, I don't even remember what it was because it's an example in the book. Wherever this data came from, the idea that it came from a Poisson distribution is a pretty decent fit. So, this okay? See? All right. We're going to do more of these next time because we still need to do a couple with... these are all the things that we've done so far have been discrete distributions, which makes it a little bit easier to calculate these things. But we also need to talk about taking data sets, a set of data where we are trying to see if a continuous distribution is a good fit for it. So we have to attack that in a slightly different way. So we'll talk about that on Wednesday. All right. Everybody have a good one. Yep. We'll talk